Okay, this week we're going to talk about pressure, and then we're going to move on to wind. There's a lot of elements to each of these, so we'll talk about them in a little bit here, just to see if we can explore them. So let's take a look at pressure. What is pressure, anyways? It's just the weight of the atmosphere. The molecules of air have weight. Anytime you get a whole bunch of molecules together, they got a whole bunch of weight. The denser they are, the more it's going to weigh. So there's an equation called which says pressure equals density and temperature, and a constant. So with that equation, you can relate temperature and density to pressure. So what you're trying to do here is understand that pressure is a weight, but there's factors that go into that weight. There's factors of density. The more molecules pressed together, the more dense the air is. There's a factor of temperature. The higher the temperature is, actually, you can get higher air pressures. But there's a caveat to that. When the air gets hotter, the molecules tend to move apart. So you wind up having lower density. So what you wind up with most times is lower pressure. Your density kind of dominates in that term. So let's take a look at a little bit of pressure this week. There'll be a lot more. You can read through it in your book and all, and some other things here. But there's a difference in pressure depending on where you are, what elevation you are in the atmosphere. Think about this. As you go up in the atmosphere, molecules fed further and further apart. They're not being pushed down by gravity as much. Gravity pulls all these molecules down towards the Earth, so they get pressed tighter and tighter together the closer to the Earth you are. The further up you are, the molecules spread out. That's called expansion of the molecules. And if you look at that, the pressure, therefore, is going to be lower because the density is lower. Oh yeah, the temperature also is going to get lower as you go up in the atmosphere. As we saw in the troposphere, temperature lowers with time, with height. So the simple equation to relate altimeter to sea level pressure is basically for every 1,000 feet you add or subtract 1 inch of mercury. So for example, here, this is in your book, so I'm not telling you anything you can't read yourself, I guess. But you can look at New Orleans, which is at sea level, and just add to Denver's observation, basically 5 inches of mercury, to bring it to be the same, that they'll match up at sea level. And we, as a meteorologist, I like to keep everything on the same surface. Not the Earth's surface, but the same pressure surface. So that's just one quick way of looking at that. Now, if you're flying an airplane, I think you want to know what the altitude is there, what your pressure altimeter reading is there, and not what sea level pressure is. Otherwise, you might be coming in a little low. So we'll look at some charts and stuff and see some things with pressure charts here. This is just a quick upper air chart. But let's look at pressure a minute here on the surface map. On the right of a surface map is your altimeter reading. It's 1013.9 here on a surface map. This is sea level pressure, actually, I'm sorry. 1012.7. But if you look at an aviation one, same one, here's Charleston, and the METAR for Charleston at this time has the altimeter right here, 30.02 inches. However, sea level pressure is 1015.8. As a meteorologist, I want sea level pressure. As a pilot, you want altimeter. They're two different things, but they're both very important. Obviously, if you know the altimeter, you can make adjustments to your standard atmosphere. If the altimeter is low, or then what the standard atmosphere is, you're probably flying lower than you might think if you were using the standard atmosphere. If the pressure is higher, you might be flying higher than what you'd think if the standard atmosphere is off that. And since the standard atmosphere is almost always going to be not quite correct, that's just one thing that's going to be throwing your altimeter off. And the other thing is temperature. Temperatures can be wrong. In the Weather Service, as far as AFSOS goes, when you look at the sea level pressure here, that you see here, 1015.8, that sea level pressure has been adjusted, not just from the standard atmosphere perspective, but from a temperature perspective. So it estimates a curve of temperature down to the surface of the Earth, which is down to sea level, which is below Charleston's observation, to come up with 1015.8. This is actually a more accurate estimate than using just a standard atmosphere. So you can see here, just looking at the METARs, you've now got pressures, your altimeter, and your sea level pressure here. You can relate these to the upper air too. So let's just take a look at upper air just a quick second here. Here's 850 millibars. When you look at an upper air map, each one of these readings is pressure, except in upper air, it's contours. So instead of looking at pressure, this is all at the same 850 millibars. But 850 millibar surface varies with height, depending on pressure patterns that go with it. So, for example, here, up in Canada, we have 473. If I add a 1 to that, it's 1473 meters. That's actually the height of the 850 millibar surface right here. From the ground. Not from this ground here, but from the actual sea level pressure. So again, yeah, 850 millibar surface is actually below ground sometimes in the Rocky Mountains, for example. But we estimate what it looks like by looking at where it's at the surface. So you can see here, you have low pressure because the winds are going counterclockwise, and this is a lower contour, 1050. So this would be 1510 or 1510. Here's 1580. So you can see there's a difference in contours, which means there's a difference in pressures. So this is pressure. So if we move on with pressure, you can get more information from it. We talked about altimeters and how they change, and depending on what the altimeter is based on standard pressure, you can be reading high or low, and temperatures have an influence on that. We looked at METAR code a little bit as well to look at sea level pressures and altimeters. Density is the final part. Density altitude is very important for an aircraft. You want to know what your density altitude is. The more dense your air is, the quicker you're going to climb. The less dense your air is, slower you're going to climb. So if you're flying out of Florida, or let's make it Phoenix, Arizona, in the summertime, your air is going to be extremely hot. That pushes the molecules apart. So you wind up with a very low density altitude, below what you would normally expect. So it's going to take more runway for you to get up in the air there than it will if you're in the middle of winter in Caribou, Maine, for example, where the air is very cold, very dense air. So just remember that the hotter the air is, the less dense the air is, the further apart the molecules are. The colder the air is, the closer the molecules are to each other at the surface of the Earth. That'll give you a good idea of how your density is changing. Now, we'll throw one more thing in here, moisture. Water vapor is less dense than actual air. So the more water vapor you have in the air, the less dense your air is going to be. So if you're flying through, like we just had here at my house, a tropical system that went by, if you were flying into Norfolk, you would have had fairly warm temperatures. Temperatures were in the mid-70s, but you would also have tremendous amounts of moisture. So your density altitude would have changed. It would be less dense. So just these are some things to think about when you're looking at this chapter and going through it and answering the questions as you're coming across here. So just looking at that, now we'll go on to one other thing I wanted to talk about, and that will be winds. Winds are related to pressure tremendously. What is wind? Well, they show it here, but think about it. If an air parcel, or say your aircraft, you move in your aircraft in 3 dimensions. You go up, you have a vertical motion, you have a sideways motion, both to the north and to the south. So that makes your motion a vector. Now, if you go with winds, that's a vector. That's a particle's motion. So when you're talking about wind, we actually, in meteorology, will think of it in 3 dimensions. There's a particle, part of the wind that's actually taking that parcel upwards. There's a particle of the wind that's taking it to the north, and there's a part that's taking it to the south. And they all are put together to look at where that parcel is going to wind up. Maybe 10 minutes from then, maybe an hour from then. But by knowing the wind direction, you can pick out where those parcels are moving. So let's look a little bit at wind direction then and how they're related. What's some things that make it? All right, one of the things I did want to mention is in a METAR, there's 2 things you're getting on wind. You're getting sustained wind, which is basically a 10-minute average of wind. And the wind is taken at 10 meters up, 33 feet up in the atmosphere. Not a lot off the ground, and probably for an aircraft, it might be actually at the height of your airplane, depending on how big your airplane is. But it's average wind over 10 minutes for sustained wind. So when you're looking at an observation and you see the wind, what you're getting is an average wind speed and an average wind direction. Oh yeah, then there's a gust. A gust is reported. There's at least a 10-knot variation between the instantaneous peaks and lulls during the last 10 minutes. In other words, you're looking at how the wind changed during that time. Were there extra winds at some time? And they're only reported if they're 10-knot difference, which is pretty significant. But if you're flying an aircraft, it might be something you want to look at. So now that we've got what a wind is, basically wind is pointed in a direction the wind is coming from. So if I tell you you have a wind 090 or from 90 degrees, that wind is an east wind. The wind is coming from that direction. If I tell you the wind speed is 10 knots, then that last 10 minutes of average to speed is 10 knots. If I tell you that there's a gust and that gust is 25 knots, then I'm telling you that somewhere during that 10 minutes or so, you had other winds that were stronger, and one of those reached 25 knots. You can also have a peak wind, and that's when it's really strong. Basically over 1 minute average of winds must be greater than 25 knots. And that's peak wind is from the observation time. In other words, if you only have one observation that hour, that peak wind could occur at any time during that hour. It usually has that in the remarks as to what time that is. So there you have a whole bunch of information you're actually learning about on the winds here. So let's go on to causes of wind. Well, what causes wind? Well, force is basically mass times acceleration. Well, Newton's laws here are, and there's unbalanced forces at work. A parcel is going to accelerate. Well, that's what happens to cause wind. There's unbalanced force. The atmosphere hates the fact that the forces are not equal. It wants all the pressures to be same everywhere. So anytime they're not, wind is going to tend to want to push the molecules from high pressure to low pressure. It's trying to fill in the gap. The greater that pressure difference, the more there is a pressure gradient. Pressure gradient is a force. So say I were to look at a weather map today. Let's just look at a surface analysis. We're going to undo this a minute. See all these contours? All these isobars right here around this, what's left of Dorian? The closer they are together is more and more pressure gradient force. Yesterday when this went by my house, I had wind gusts over 50 miles an hour, sustained winds of 40 miles an hour. Well, I wasn't anywhere near the actual center. I was up here and the center went down here. There was a pressure gradient across my house, and the winds were trying to move in to get into this area. So if you just had pressure gradient as the only force acting on an air parcel, the wind would always be from high pressure to low pressure. But there's more than one force. So now that we've started this, what's the next force? Coriolis Force. Coriolis Force is weird. I'll admit it. Say you are at the North Pole. It takes you still 24 hours to rotate all the Earth all the way around at the North Pole. If I put you at the equator, you're still 24 hours to rotate all the way around. Yet you didn't hardly move at the North Pole, did you? But at the equator, you moved about 24,000 miles. So your speed was much greater. So what happens is when we look at a weather map or look at anything, the Coriolis force is much greater at the North Pole because it's trying to account for this change of motion between the equator and the pole. That's the Coriolis force. In the northern hemisphere, it always acts to the right of the wind. So say in this case you have a pressure gradient from high pressure to low pressure, and the wind is coming from the west. The Coriolis force is going to want to make that wind turn more towards the south. It's going to push it that way. So those two combined provide changes to wind. They show it right here how the ball moves in very different directions when you're at the North Pole, at the equator, how it would move. So what is a geostrophic balance? Well, a geostrophic balance is just those two forces, the Coriolis force and the pressure gradient force. And when they equal, the parcels of air will move right along either an isobar, a contour. So let's take a look at isobar, at contours. You're up a little higher in the atmosphere. There's some other impacts down in the low levels of the atmosphere. But you'll notice here, they kind of go right along with your contours. They're moving pretty steadily. The more the gradient, the better they go. Let's look even higher up. We'll go to 300 millibars. Now look how they really flow with your contours. Oh yeah, there's a pretty good pressure gradient in here and stuff too. So helping your motion to be even faster at this level. But you can see they do flow with the contours, right along with them. Kind of nice how that worked out, isn't it? But if I go down to the surface, there's something else that gets added in. And that something else will be friction. But one other thing we got to talk about too here is centripetal force. Okay, what's centripetal force? Let's take a thing when you drive around a curve. You're driving that car on a curve. What is keeping you on that curve and not making you go out into space or not be forcing you to go in a straight line? It's centripetal force. It wants to keep you in motion. So the gradient wind is centripetal force. When you have a strong pressure gradient and you wind up going in circles, it's a centripetal force that's being added in there, as well as the Coriolis, as well as the pressure gradient. So those three factors then combine to cause circular motion in the atmosphere. And then finally, when you get the final piece of it, you get the friction. Friction is going to be greater, say, at the mountains, at the surface of the earth, when it's very rough terrain. All of that is going to tend to maybe slow something down. It causes the wind to kind of go towards low pressure more. Instead of following the contour, it pushes it in towards. So the winds are actually moving towards low pressure. And the further up in the atmosphere you are, the more and more you're away from that friction. So friction doesn't have as much of a role up in the higher atmosphere. You'll see the winds kind of blowing along the contour here. At the surface, they're blowing in. Oh yeah, if you're coming across the mountains and all that, that's going to impact your molecules' motion too. It's going to change the direction of motion. That's a force. Air hits the mountain is friction, and a mountain will cause that air parcel to rise or cause it to go to the left or to the right to get around it, like it does on a building. I don't know if you saw the Weather Channel, but the other day they had a person between two high-rise hotels, and they were getting a lot of wind there. The reason they were getting that is all the pressure gradient was hitting those hotels. It had to go somewhere, those molecules, so it flowed between the hotels. That can happen in passes in mountains. So you can have a much higher wind speed, for example, there than you would in other areas. So now that we've talked about all of these things, also you have vertical motion, say the wind particles are coming together. So I hope you got a little bit out of this. Just give you an example, you see your counterclockwise flow, but the winds are actually flowing right to kind of towards low pressure here, and that is friction that's pushing them in there. So I hope you got something out of this. Let me know if you have any questions these weeks.